In this video, I will briefly introduce our work, a keylogging inference attack on air tapping keyboards in virtual environments that is published in IEEE VR 2022. The features offered within the AR head-mounted displays allow diverse use cases including simulation, training, entertainment, and assistance. To support such diverse use cases, these technologies offer new interaction methods with the virtual environment. To fully integrate AR technologies to our daily lives, the research community is working on more natural interaction methods for more convincing perception. The methods include but not limited to voice command, hand gestures, hand and gaze tracking. In this work, we take a closer look into the privacy impact of the input entry methods facilitated by hand tracking. In our system model, we consider a victim user wearing an AR HMD capable of hand tracking. The user types on an AR keyboard that is only visible through the AR glasses, and the adversary tries to recover what the user has been typing on the private virtual environment. In our threat model, we consider three scenarios. For all scenarios, the adversary obtains the same data, but the data collection medium changes. Our attack pipeline consists of 5 steps: deep key tap localization refinement, candidate key center generation, candidate keyboard reconstruction, and best to worst ordering. In the first step, we leverage the fact that the hands follow a certain pattern while tapping on the AR keyboard. Based on this, we localize the key tap specific patterns on the data stream. The coordinate system of the low-level data changes as the hand tracking sensor is placed in a different position. Therefore, we first pre-process the data. Then, we perform temporal localization on the data stream using a multi-head CNN. In the second step, we refine the localized key tap positions. We know that the key tap points lay on a plane in 3D. Therefore, we estimate a keyboard plane for the candidate locations from the first step. Then, by following the hand traces, we refine and reduce the dimension of the key tap points on the estimated plane. When each key center on the AR keyboard is treated as a cluster centroid, each key tap point should belong to the cluster of the associated key. Based on this, we argue that proper clustering of the found key tap points partitions them into the associated key clusters. For such proper clustering, the ideal thing would be knowing the number of unique keys in a session. However, this is not the case in our system model. To address this issue, we apply agglomerative hierarchical clustering on the key tap points and generate a set of clusterings with a varying number of clusters. The cluster centroids are treated as candidate key centers. In the fourth step, we find candidate keyboard reconstructions using the candidate key centers. To achieve this task, we account for the possibility where each candidate key center may correspond to any key on the keyboard. At each session, the coordinate systems of the hand tracker and the adversary's AR model change, and there exists a similarity transform between these coordinate systems. Once we found the transformation, we project the key tap points onto the keyboard model. As a result, we map the key tap points to their corresponding keys on the AR keyboard. In the previous step, we obtain countless inferences as an output of this exhaustive process. Many of those inferences are inaccurate due to the incorrect pairings. Although the search space is still significantly reduced, it is still infeasible for adversary to consider all reconstructions. However, accurate reconstructions have certain characteristics which we measure with inference measurements. In this step, we filter out the inaccurate keyboard reconstructions and order them from best to worst using the inference measurements. To evaluate the performance truly, we conducted experiments assessing the performance of the individual steps as well as the end-to-end pipeline. The experiments involved 5 participants. The accuracy of the attack is measured with normalized Levenshtein similarity and its HOP and TOP-K variations. Keystroke detection stage of our pipeline includes the first 2 steps: deep key tap localization and key tap localization refinement. For the evaluation of deep key tap localization, we trained our multi-head CNN as a binary classifier. Then we performed predictions on the testing split. The prediction procedure takes the set of input segments and output found key tap events with their confidence scores. Given each ground truth key tap segment, we associate the found key tap events with ground truth segments which are closest in time. We also keep track of the intersection or union of each association. We eliminate the associations with IUU values less than the given threshold. The precision recall curves for left and right hands here show the results with varying thresholds. As we expected, a small threshold yields a better classification model. The bar charts here show that with key tab localization refinement, we significantly decrease the number of false positives while slightly affecting the true positives. Let's move on to the evaluation of key identification stage, which includes the last 3 steps of the pipeline. For this set of evaluations, we collected 4 types of data from 3 participants. The plots here show the accuracy results we obtained with different HOP and top key variances. Within the first 500 reconstructions for email and R5 datasets, our key identification were able to reach 100% pinpoint accuracy. Similarly, we were able to reach the 100% accuracy within the first 500 reconstructions for R10 and R15. Lastly, we evaluated the end-to-end pipeline. This table shows our results for all datasets and varying HOP and top K configurations. As the number of reconstructions increases, the accuracy also increases. The maximum pinpoint accuracy achieved over all reconstructions is 68% for email, 76% for R5, 87% for R10, and 62% for R15. As we can see here in the green columns, we are able to list those most accurate reconstructions within the top 500 reconstructions. This figure shows a sample inference from the email dataset. Our attack was able to recover most of the sentences. As a countermeasure, we propose and analyze dynamic positioning. For x and y dimensions, we define a translation vector t. After each keystroke, we form a translation vector by randomly choosing the angle and the length. Then, we simply slightly move the keyboard in the virtual environment. With this method, we protect against the key identification stage of the attack. Thank you for your kind attention. Please use the listed email for your questions.